Well, here we go. We've finally been working our way up to this moment here as we've been, experimenting with exponents and all the goofy rules associated with them. And we're finally ready to dive into exponential functions. And today we're going to focus specifically on exponential growth. Tomorrow we'll have a separate lesson on exponential decay and really tie the two together. So the first thing is, how do we tell the difference between an exponential function versus, a linear function or a quadratic function or a rational function or really any other type of function we've experienced up till now? So the general form of an exponential function says y equals a times b raised to the x. Okay. Of course, the x and the y are your variables, and then the letters a and b are what we call constants. They just represent just numbers. And there are really three conditions that have to be met. Number one, and probably the most important one, is that the variable must be in the exponent. And that's really where the name comes from, exponential functions. All right. Now, the value of a cannot equal 0. Okay. Other than that, a can be anything. It could be positive. It could be negative. It could be an integer. It could be a decimal. It just cannot be 0. And then that b value, it must be positive. With one exception, it cannot equal 1. Okay, so what we're going to see here today is all of our b's are going to be greater than 1, and that creates this growth model we're looking at. All right, and then tomorrow the b's they're still going to be positive, but they're going to fall between 0 and 1, and that's what's going to create that decaying model we're going to look at. So growth means the graph is going to increase at an increasing rate. Decay means it's going to decrease at a decreasing rate. So those are the two functions we're looking at. And one thing that's really interesting about both of these functions is they have a horizontal asymptote. Okay, and we like to say the graphs are asymptotic to the x-axis. In other words, the arrow on the left side of this function or the arrow on the right side of that function, they progressively get closer and closer and closer to the x-axis without ever touching it. Okay, so we're going to use those three conditions we just talked about to help try to distinguish which of the following functions are exponential. All right, so we'll go through our checklist here. Looking at the first equation here, our variables in the exponent, check. Our a is not 0, check. And our b value is positive but not equal to 1. So I think we've met all of the criteria, and we're going to say, yes, this is an exponential function. Now, in the second one, I think the first thing that fails is the location of the variable. See how the variable is not in the exponent? So we got a big fat no on our hands here. Not an exponential function. All right, in our next example, the variable is in the exponent, check. The a is not 0, check. And our b value is positive but not equal to 1. So that's definitely an exponential function. And in this particular case, it happens to be a decay function, whereas this first one over here with the 2, because 2 is bigger than 1, it's growth. And then over here, the 1/2 falls between 0 and 1, so we'd say it's a decay model. All right. On this next one, this is actually, if number 2 was an example of a quadratic function, okay, it wasn't an exponential. Number 4 is an example of a linear function. All right, and right out of the bat, check out where that variable is. It's not in the exponent, so we know it's not exponential, and it fits that y equals mx plus b format. Number 5 is not exponential either. This is an example of something we call a rational function. Pretty much anything that looks like a fraction where you have a polynomial on top and a polynomial on the bottom is going to be rational. Okay, this number 6 is an excellent exponential function. We've got our variable up here in the exponent. Our a is not equal to 1, and our b value is positive but not equal to 0. So we got a huge emphatic yes on that one. This one is exponential. Similarly, our next one here, we've got our variable in the exponent. Our a is not 0, and our b value is positive but not equal to 1. So we've got another emphatic yes to an exponential there. And our last one fails right out of the gates. Notice where the variable is. It's not in the exponent, so it's not exponential. This is an example of what we call a cubic function because of the degree there. That's a third degree polynomial. So how do we exactly interpret an exponential function? What kind of information can we gain from it? So the value of a is really, really special. That what I like to call the leading coefficient measures the initial amount. So maybe we're using this function to describe or model the population of Hamburg, or the number of Skittles you've ate throughout the day, or anything you can imagine. The A is going to represent the initial amount. Now, the B value is even more important. It is, by definition, equal to 1 plus R, okay? Where R is the rate that the function is growing or increasing. So let's look at a couple of examples we'll just make up here on the fly. If I had y equals 10 and 1.04 raised to the t, I'd say that I've got my initial amount of 10, and then we're actually growing at a rate of 4%. Now, how do you look at this and get 4%? What are you talking about, Mr. Hill? Okay, well, think about this. The value of b is equal to 1.04, and that's equal to 1 plus r by definition. Well, what if I looked at this equation and I solve for r? I would just subtract 1 from each side, right? That's 0.04 equals r. And like a lot of our rates, we're going to move the decimal 2 places to convert it to a percentage. So we're getting 4%. We're increasing at a rate of 4%. Okay, so we're going to put that to practice and introduce you to this idea of frequency at the same time. So let's assume that x is measured in years. Okay, let's assume that x is measured in years, and maybe I'm going to try to zoom out and make this even a little bit bigger, but it's okay. Okay, so we look at the very first one. This 1.4 is going to be your initial amount, so that's 1.4. Okay, now this is your b value, and what I'm going to do is I'm always going to set that equal to 1 plus r. Now, a lot of these, you can just go ahead and do them in your head. If you feel comfortable doing these in your head, go for it. Subtract the 1, you're going to get 0.08 equals r. In other words, we're increasing at a rate of 8%. Now, how frequently are you increasing at a rate of 8%, each year, each month? How often? How frequently? Okay, here's where that exponent comes into play. See how it's x divided by 3? So it's going to be every 3 years. We're increasing at a rate of 8% every 3 years. Okay. In our next example here, my initial value is 25. We're increasing at a rate of 15%. How often? Every 5th year, or every 5 years. All right, third one here. 100 is my initial value. When I see 1.23, I know we're increasing at a rate of 23%, and that's happening every 10 years. Every 10 years, or every 10th year. All right, the next one's a little bit trickier. Not at first, per se. You see the 4, and you're like, all right, my initial value is 4. But what do I do with the base? Remember what we did on that first example. Take your base, set it equal to 1 plus r. Subtract 1. Oh my goodness, 1 equals r. Now what do? You still have to move the decimal place twice. You're going to end up getting 100%. Okay? In this case, the x up there, that exponent, isn't being divided by everything, so we would say each year, or every year. So 100% each year. Now, believe it or not, when something increases 100%, we say that the amount is doubling. Okay, so anytime you talk about doubling, we want the base to be a 2. Or, another popular one is if the base was a 3, then we know it's tripling. That's another really popular one. Let's sink our teeth into go ahead and graphing our first exponential function. And what I'm going to do is I'm going to help get you started with the table of values. And for my x's, I'm going to start with -4, and we're going to go crazy. And we're going to use all these x values up to +4. Now, to make our life a little bit easier tonight, you're more than welcome to use your calculator. I went to y equals. We'll enter in the function 2 raised to the x, starting at -4. Now, if I was evaluating this in my head, I'd say 1/16th, and my calculator converted that to a decimal to get 0.0625. So that's a very, very small number. That's very, very hard to graph. We'll just do the best we can. And then when x equals -3, we get a y value of 1/8, which is 0.125. Okay. When x equals -2, we're going to get 1/4, which is 0.25. Then we get 1/2, which is 0.5. Anything to the 0 is 1. 2 to the first is 2. 2 squared is 4, and then 2 cubed is 8, and 2 to the fourth is 16. So now what I'm going to do is I'm going to very, very, very carefully graph those the very best I can. Let's see. Oh my goodness. How do you do 0.0625? You basically just put it one super tiny smidge above that x-axis here. Super tiny smidge. And then at -3, we're basically about the same. Let's see, 0.25, and then at -1, it's up all the way up to a half. So we're very slowly climbing, very slowly climbing. Then we get to 0, 1 and 1, 2, and then watch this rabbit take off. We're going to get to 2, 4, and then we're going to jump all the way up to 3, 8, and we're starting to gain some momentum, and we get all the way up here to 4, 16, and I'm going to try to connect these as carefully as I can. Notice being very, very careful not to touch that x-axis. Talk about that in a second. And yeah, I am not real great at these. Trying to be as smooth and as careful as we can. We'll put some arrows on the ends here. And this is an exponential growth function. And you'll notice the function is not just increasing, but it's increasing at an increasing rate. Couple of sidebars. Like now, if I drew a linear function like this, I'd say it's increasing at a constant rate. The graph we just drew is increasing at an increasing rate. If I drew something like this, and we'll see functions similar to that down the road, that one's increasing but at a decreasing rate. Okay. Now let's look at some special characteristics on this graph. There is what's called a horizontal asymptote. Okay. I'll try to do this in pink. Notice the graph gets very, very close to the x-axis, but it never touches the x-axis. All right. It's kind of like an invisible fence that you might have in your yard. Your dog's, certainly going to test his boundaries, and he gets very, very close to that fence, but hopefully he never touches it. And so the equation is y equals 0. Now the domain, you'll notice because of those arrows, we do extend infinitely to the left and to the right. So the domain is all real numbers. Now, because of that asymptote, the range never goes below 0. So our range is going to be from 0 and then upwards to infinity. So 0 is my lowest, infinity is my highest. So those are some special characteristics we'll talk about from time to time. We're going to wrap today up with 2 fun little word problems. The number of mosquitoes at a lake where time is measured in days is modeled by this equation. How do you know this is exponential? Well, go through your checklist. Your variables in the exponent. A is not 0. And B is positive but not equal to 1. So we've checked all 3 boxes. How many mosquitoes are at the lake initially? Okay. That's going to be your A value. So we know right out of the gates, we initially have 1,020 mosquitoes. That's more than we care for. At what rate is the number of mosquitoes increasing? We'll take your B value, set it equal to 1 plus R. Subtracting 1, oh my goodness, look at these mosquitoes. If you move that decimal 2 places, they're increasing at a rate of 305%. I'll tell you what, I am not visiting that lake. I'm not visiting that lake. No way, Jose. Me and mosquitoes do not get along. If this rate continues, how many mosquitoes will there be 10 days from now? Well, the good news is they said time is already measured in days, so we simply just need to substitute a 10 in. Do be careful, though. Sometimes they will change the units on you, and then we need to adjust accordingly. So we're going to say, using good notation, that m of 10 is equivalent to 1,020 times 4.05 raised to the 10th power. We'll go ahead and test this out, see if you get the same answer as I do when we plug it into our calculator. 4.05 Raise that bear to the 10th power. Whoa. Man, that is a big number. Where do my commas go? I think I'm getting 1,211,017,458. How about that? Yeah, that's more mosquitoes than we care for. So you got to be careful. Watch out for that lake. All right. The amount of snow in Mr. Hill's driveway is modeled by the following equation, where T is measured in hours since midnight and A of T is measured in cubic yards. How many cubic yards of snow were in the driveway initially at midnight? And so in this case, whenever you see the word initially, in this case, T was defined as hours since midnight, we're implying that T equals 0. So if you ever got in a pickle, you could just substitute a 0 for T, and use your calculator to evaluate this. But I think we can just do it by identification. We'll say there are 45 cubic yards of snow in the driveway at midnight. That means we're probably going to have a snow day. At what rate is the amount of snow increasing? Okay. Again, you may be able to do this one just by looking at it. But just in case, we're going to take that base value, set it equal to 1 plus r, subtract that 1 over, and then move the decimal place twice. So we're getting about 36%. Snow is coming down, ladies and gentlemen. We can smell a snow day coming. If this rate continues, how many cubic yards of snow will be in the driveway at 6:30 a.m. when we try to leave for school? So what we're going to do is we're going to substitute a 6.5 because it's 6.5 hours. So we could say A of 6.5 is equivalent to 45 times 1.36. Oh, that just reminded me. I forgot to answer part of part B. Let's shimmy back. I didn't answer this question, how frequently. You remember how the exponent's being divided by 2? Remember what that means from earlier in the video? We should say, okay, if that's divided by 2, that's going to set the frequency. We're going to say 36% every 2 hours. So it's not coming down quite as fast as I implied earlier. So it's not 36% each hour. It's just 36% over a 2-hour time span. Anyway, let's go ahead and let's just plug this into the calculator and see what we get. All right, my calculator's telling me, let's see here. I got about 122. If we go 3 decimals, that'll be 240. All right, cubic yards. And I'm telling you what, ladies and gentlemen, that probably means day off right there. That's a lot of snow. So I'll tell you what, we threw a lot of information at you tonight, okay? So really pour over these notes, okay? Review them very carefully. And let's go ahead and we'll apply it tomorrow in class and kind of get a gauge of how we're feeling. Have a great night.